So yeah, in this talk, I'm going to share my journey, or I should say our journey, about horizontally scalable controllers. Normally, a controller is not scalable, but we managed to build controllers scalable, horizontally scalable over a cluster. So in this talk, yeah, I'm going to share how we got to the horizontally scalable controllers. I will first talk about the captain of this talk. Then I'm going to share infos about the hobbyfarm project where we built these controllers for. And also I will share the initial architecture. Afterwards, I will talk about how we got to sharding, which is one of the main core ideas of horizontally scalable controllers. And finally, of course, I will talk about our solution. So first, the captain, this is a little bit about me. So I'm a system engineer at SVA. I'm based in Bremen, which is 1 hour from here in Hamburg. I like to give container and Kubernetes trainings. And also I like open source. So this platform and all of the things I will share today are open source in the project hobbyfarm. And for the next 30 minutes, I'm your captain here. So the hobbyfarm project is a small project. It's open source. You can Google it on GitHub, github.com/hobbyfarm. It's a browser-based training platform. So whenever we give a Kubernetes training or any other DevOps training or any other IT training or even non-IT trainings, we use this platform to provide the content for the users to learn. So basically, what is a pod? Maybe that can be a start. Going through theory is not quite enough. So we want to try to enable the user by giving him infrastructure. And so the platform spins up pre-configured environments on any cloud or even on-prem. And then the user has this kind of view. On the left side, he has like the content. He also has like clickable boxes where he can execute code directly. And on the right side, he has direct access to the virtual machines. Even multiple virtual machines are possible there. So why are we even taking this journey? I mean, our application on sunny days is gliding smoothly through the water, and life on board is very good. So our mood is very good. But as the number of users grew, they basically pulled our controllers underwater. And our mood began to disappear. So why is this? The initial architecture of hobbyfarm was we had basically one pod running inside a Kubernetes cluster that used CRDs and controllers that control these CRDs. So basically, whenever a virtual machine is created, we create another resource in the cluster, and a controller then handles all the connections to the cloud and spins up the virtual machine, and deprovisions it at the end. This approach was very monolithic. We had like multiple controllers inside a pod, which is like an anti-pattern. Also, we had like APIs that were provided to access all of the data inside of the front end, so the user can actually access the virtual machine. What is the advantage of this approach? Actually, I don't know. It has multiple challenges, which is like scalability, one of the main issues. If we have like multiple hundreds of or thousands of users, the controllers are very slow, and spinning up a new virtual machine takes very long. So also updating components and libraries is a problem because we have to update them for all of the controllers at the same time in a monolithic approach. Also resource utilization. If we want to scale this up, we would have to scale all of the controllers, even if only one controller is the bottleneck. Yet also testing is a problem because it's all in one weird monolithic container. And there might be many more. Those are just like the main points. So on our journey, we set sail, and we started with our monolithic application, and where the Kraken pulled it underwater. And along our journey, we discovered some empty villages with some leftover huts. And one of the huts actually contained information about microservices. So we discovered that microservices might be a better solution and a better approach. This technology seems a bit dusty. I think it has been around a little while. So the first approach is migrating to microservices, obviously. So now we have multiple pods, each having one controller. The advantage is, of course, we have a scalable API, and the challenge here is we have controller concurrency if we don't do such things as leader election. We cannot start multiple controllers that overview the same resource because then multiple controllers might interfere with each other, and two controllers might to change the same resource. That is a problem. So common approach is, as I said, leader election. So we elect leaders among the different CRDs, basically. And so only one controller is started. Advantage here is, of course, we have a scalable API, but controller scalability is also a problem. We only have one controller running. So those are not scalable controllers. Also, the leader election takes startup time to elect the leader. And we have a delayed reconciliation during re-election. So if the leader fails, we have to re-elect, and in this time, no reconciliation is happening. So, and only leader does the work, so the bottleneck is still there. So the next point on our journey is that we met a friendly kraken in the ocean, and the kraken juggled multiple balls with his 8 arms. And he brought us the idea of sharding, threading, sorry. And just like the kraken, we could handle multiple objects at the same time. So to improve our controllers, we will implement threading. So on the left side, I have a controller, and we just have a little work queue in there. Also note the little crown on the right side. This means this is still the leader. We only have one controller running at the same time. And instead of using one worker, we just use multiple workers to speed up the reconciliation. That works. So the advantage is, of course, still the scalable API, a faster reconciliation because of the multiple workers working. Challenge is still controller scalabilities. We can still not overcome the leader election issues. So leader election still takes startup time. So we still have the delayed reconciliation during re-election. Those applied last time. And only leader does the work again. So all of the other are basically sleeping and doing nothing. So a common approach here could be to implement a message queue. So have like an external message queue and have multiple replicas with multiple threads that just get the next item from the message queue. The problem here was that we didn't want to rely on any message queue being installed in the Kubernetes cluster because we are an open source project, and then we would have to basically rely on any message queue, and we didn't want that. We wanted the replicas to basically manage themselves. Advantage here is scalable API, scalable controllers this time, faster reconciliation. We don't have leader election, so we can have multiple replicas running the controllers. Challenge here is we have the dependency, and we might have concurrency issues if the message queue is not implemented correctly. But also, I want to point out, this is a valid solution. We could have just chosen those, but we went a little bit further. Also on our journey, in the forest, we met a lumberjack. And he was a very strong lumberjack, but he was not strong enough to carry a whole tree on his own, as I guess many of us are. So he cut the tree down in multiple pieces of wood, and by this concept, he introduced sharding to us, splitting down things. This is the lumberjack, So sharding is the next step on our journey. And we basically got this concept from databases. Databases have been doing sharding for a long time, actually. So on the left side, we have a big database. It grew because there were many people putting data into it, so it got slower and slower. And by sharding the database, we now have multiple smaller databases with a smaller subset. All of the subsets combined basically hold the same data as the database on the left side. But all of the smaller databases can access the data much faster and process it faster. So advantage here is this is actually horizontally scalable. So we can spread this about multiple replicas and multiple nodes, actually. It has improved performance, of course, because the smaller databases can access the data faster. Challenging could be the data access, because now we have multiple sources of data and we don't know, or might not know, where the data is stored. So there are some concepts that overcome this issue. So we could shard by range. Basically, we could take the index and just say, for the first 25 items, use this database. For the next 25, use the second database. So we could split up the data onto the 4 databases we now have. A problem or an advantage could be we have an easy mapping method, but the challenge is hotspots. So if we have many new objects in the range of 76 to 100, only the Ford chart would basically work on them. The same problem would apply if we take this concept to controllers. So there's another way of doing this, and this is by hashing the key. So now we take a hash of the key, and if we take a good hashing algorithm, it's equally distributed, and hotspots are not a problem anymore. So we just have this simple hashing algorithm. We take a hash of the name or the metadata.name or the ID. We hash it by the count of replicas we have, in this case 4. So if the hash modulo 4 in this case equals 1, we go to shard 1. If it equals 2, we go to shard 2, and so on for all the replicas we have. This is a scalable approach. So we also have easy mapping. This time it's not by ranges, but we can calculate it basically, which shard the mapping is applied to. This is equally distributed if we take a good hashing algorithm. Challenge might be CPU time for hash calculation, but I mean, it's not the hard calculation to calculate a hash. So we finally reached the marked spot, but we dug day and night, but we can simply not find the treasure. So where is the treasure? The treasure is that, on our way, we found the hut, which brought us microservices. We found the Kraken that introduced us to the concept of threading, and we came across the Lumberjack, which introduced sharding to us. So basically, the journey we took was the real treasure all along. So how do we now build this horizontally scalable controllers? So now we had this sharding algorithm. So whenever an informer event applies, we just take the hash of the metadata.name of the object that needs to be reconciled. So whenever a resource is applied or changed, we now then calculate based on the hash on which shard this applies. So we take the hash that we currently calculated, take it modulo the number of replicas we have in total. And if this equals I, so I is the ID of the replica this is running on, then we add this to the local work queue. If this is not true, so if this is, for example, for the second, third, or fourth shard, then we do just nothing. So we do not add it through the local work queue. And by this way, and we only, of course, work on the local work queue. There's an image on one of the next slide. So what hashing algorithm should be used? So we need consistency over all of the replicas, of course. We need a good distribution, and we need to also be fast, so the CPU time overhead is reduced. And we do not care about cryptographical safeness here. So this has nothing to do with cryptography, so we only need one that fulfills all of the above. There are 2 we came across. This is FNV, and also there's Murmur 2 that fulfill all of those. They might be unfamiliar to you, but those are used when you want to maybe have a good distribution that can be fast calculated. And we choose FNV because of its existing Go implementation, and the controllers are written in Go. So this is now the final picture of the sharded controller. We have the Kubernetes API, we have a shared informer, and then we have this sharding algorithm that is basically listening for all the changes. And if the sharding algorithm refers to true, referring to one of the last slides, we add this to the work queue. So this only applies if my current replica should basically reconcile this. So if I have 4 replicas, only one of them is going to reconcile it, so we don't have concurrency issues. And then, of course, we still use threading, so we have like multiple workers. We build it so that you can configure how many threads you want, and this concept can be scaled. So we have a scalable API, we have a scalable controller. This is equally distributed because of the sharding algorithm we implemented. We don't have leader election. We can basically scale to 1 or to n, so basically all of unlimited. Challenges could be identity management, so which replica am I? Because I only want to reconcile the shards that were mapped to me. And also, what replica am I? And also detecting scaling events, so what happens if we now scale a replica higher or lower? So how many shards are available? Because we need this information for the sharding algorithm. So identity management, I'm replica 1, I'm replica 1. This is, of course, a concurrency issue, so we don't want that. So in Kubernetes, there's the concept of stateful sets, so we can basically map an identity to the pods. So we have controller 1 and controller 2 that are managed by the stateful set. So now, if we want to detect scaling events, let's say we have these 2 replicas, so we know n is equal to 2. Now they both watch the stateful set and watch for changes on the stateful set. So now if a change applies, so a third controller comes up, it is given the identity of 3 by the stateful set, then of course the n equals to 2 is not valid anymore, but because of the informer changes, we now know that n is equal to 3, basically. Basically, thank you for being in the crew. That was my talk. I did not exceed the 30 minutes, I guess. But yeah, small.
Let's have a round of applause for Jan. I really enjoyed how you showed that you took pragmatic decisions instead of like throwing everything, all of the complexity up front. We do have a couple of questions for you. Worry not. Okay, so the first question is, how do you rebalance the data when changing the number of shards that you use?
So when changing the number of shards we scale up or down. That is basically a change of number of shards. And we do not rebalance the data, but the hashing algorithm just basically calculates the shard that is where this is reconciled. So when another change in the informer comes, it is just reconciled on the new shard it is mapped to. So it's calculated whenever a change happens. So we don't have faulty data mapped to a shard or a replica.
The next question is, does the controller equal the K8's master node? I think this is just a clarification.
Yeah, no, controller means pod here. So a normal Kubernetes controller that handles changes on CRDs, basically.
Okay. The next question is, how many healthy nodes do you need for a successful leader election? What happens if that number is not reached?
I mean, we are not doing leader election, but I can also try to answer these questions. Healthy nodes. I mean, nodes does not also have to do with leader election. I'm not quite getting the question. Is anyone in the crowd here that phrased this question and can clarify?
It's all right. They can catch you after and chat to you.
Catch me after, yeah.
Yeah. And the last question is, have you also tested MD5 as a candidate for your hash functions? If so, what are the drawbacks?
Yes, MD5 would be also a valid approach, but the distribution, actually, I read like a paper on this, and the distribution is more equal on FNV because MD5 cares about cryptographical safeness, and FNV does not. Basically, it cares about distribution only and all of the other factors I mentioned.
And then there's one more last-minute question came in, and the question is, based on what do you spin up an additional worker?
So workers are not spin up. So we spin up. We basically do not spin up new controllers currently. That would be a valid approach to also auto-scale those based upon the load. So you would just take the load of the controllers basically, and if they are too slow reconciling, you could define a threshold and then auto-scale on that. But we are not currently doing this. We have implemented that you can define a fixed amount, and if that does not work for you, you would have to basically increase or decrease it.
And one more question is, what property are you hashing?
We are hashing the metadata.name of the object that is being reconciled. That is consistent data over all of the replicas. And it does not change. So, and it's unique.
That's all the questions we have. Let's have one more round of applause for
Perfect.
Jan.
Thank you.